AI moved past the initial promise and setbacks of rule-based systems and expert systems. The 1980s and 1990s witnessed a crucial transformation in the field. The limitations of symbolic AI led researchers to explore alternative paradigms, notably connectionism and data-driven methods. This era marked a decisive shift toward machine learning and neural networks, culminating in breakthroughs such as the backpropagation algorithm that laid the foundation for modern deep learning. During the early decades of AI, symbolic approaches dominated research. Researchers relied on hand-coded rules and logic to emulate human reasoning, which had shown success in controlled domains, but struggled with real-world complexity. Limitations of purely symbolic AI, often characterized by brittle performance, poor scalability, and an inability to adapt to new or noisy data, spawned a rethinking of how intelligence could be realized in machines. In response to these shortcomings, the connectionist approach emerged as a more flexible and resilient alternative. Connectionism aimed to mimic the architecture of the human brain by modeling networks of simple processing units, whose collective behavioral patterns create intelligence. This approach shifted the focus from explicit rule encoding to learning directly from data. The renewed interest in neural networks promised systems that could recognize patterns, adapt to new inputs, and improve autonomously, a stark departure from the static, rule-based systems of the previous era. A pivotal advancement during this period was the resurgence of interest in multi-layer neural networks, enabled by the development and popularization of the backpropagation algorithm. Early neural network models, such as the perceptron, encountered significant limitations. Notably, Minsky and Papard's influential critique in the late 1960s highlighted the inability of single-layer perceptrons to solve nonlinear problems. This criticism had relegated neural networks to the sidelines for some time. The situation changed dramatically in the mid-1980s with the work of David Rumelhart, Geoffrey Hinton, and Ronald Williams. They demonstrated that backpropagation, a method that computes the gradient of the loss function with respect to network weights, could be used to effectively train multi-layer networks. By iteratively adjusting weights to minimize error, neural networks could learn to model complex, nonlinear relationships from data. This breakthrough provided a practical mechanism for training deep neural architectures, reinvigorating the field and establishing a clear alternative to symbolic systems. Backpropagation's impact was profound in several respects. It showed that neural networks were not inherently limited by issues of architecture or learning potential. Rather, the challenge lay in finding the right optimization strategy. This revelation spurred a wave of research into network architectures, activation functions, and training procedures, all of which form the bedrock of what would evolve into modern deep learning. The renewed focus on learning from data manifested in a series of landmark developments. Across the 1980s and 1990s, multi-layer perceptrons, once discounted for their lack of training methods, returned stronger than ever. With backpropagation providing the means to effectively train these systems, researchers demonstrated neural networks capable of solving problems that extended far beyond the capabilities of earlier single-layer models. Researchers experimented with various architectures, including feed-forward networks, recurrent neural networks, and later, convolutional neural networks. These explorations laid the groundwork for specialized tasks, image and speech recognition. For example, where the hierarchical feature representation became instrumental in handling complex data. Besides backpropagation, developments in optimization techniques, such as the use of momentum and adaptive learning rate methods, further enhanced the training of neural networks. These improvements increased network convergence speed and stability, allowing neural networks to be scaled to more sophisticated problems. Alongside deterministic approaches, probabilistic methods began to merge with neural network research. Methods that probabilistically interpreted data allowed networks to better handle uncertainty and variability, thus bridging the gap between purely data-driven approaches and the requirements of real-world applications. The conversation about learning methods expanded to include kernel methods and support vector machines. Although these were not neural networks per se, they shared the data-centric philosophy that emerged from the limitations of symbolic AI. Their successes in pattern recognition further solidified the shift toward a learning-based paradigm in AI. The progress in machine learning and neural networks during the 1980s and 1990s was not solely theoretical. It was also bolstered by practical improvements in computational hardware, although the computing power available during this period was modest by today's standards. Incremental advances in processing speed and memory allowed for more complex simulations and larger datasets to be handled by neural network algorithms. These improvements facilitated a transition from toy problems to more applicable, real-world challenges and enabled a robust experimental validation of learning theories. Experimental platforms and simulation environments grew more sophisticated, providing valuable test beds for researchers to refine their models. This period also saw the creation of benchmark datasets and tasks that would become integral to measuring progress in machine learning. A tradition that continues today with datasets like MNIST and CIFA, R. The reemergence of neural networks and the success of backpropagation had a transformative effect on academic research and the broader culture within AI. Funding agencies, which had retreated during the AI winter, gradually shifted their focus back to machine learning projects as their potential became undeniable. Conferences, workshops, and journals began to prioritize learning-based methods, and academic curricula integrated these techniques as core elements of computer science programs. The debate between proponents of symbolic AI and connectionist approaches also stimulated a fertile academic discourse, while the symbolic approach was not discarded entirely. The connectionist paradigm promised greater flexibility and a closer resemblance to biological cognition. This comparison sparked interdisciplinary research, bridging insights from neuroscience, psychology, and computer science to tackle the intricate problem of artificial intelligence. While the breakthroughs of the 1980s and 1990s did not immediately yield the pervasive, transformative applications seen today, they laid a critical foundation. The principles of learning, pattern recognition, and optimization developed during this era directly influenced the explosive growth of deep learning in the subsequent decades. Many of the architectures and training techniques refined during this period have been scaled up and enhanced with vast datasets and unprecedented computational power. The iterative process rooted in empirical success, algorithmic innovation, and interdisciplinary collaboration ensured that the field remained dynamic. It evolved in response to both technical challenges and the pressing need for systems that could learn and adapt autonomously. The legacy of backpropagation and early machine learning research is evident in modern language models, computer vision systems, and countless other applications that redefine our interaction with technology. Conclusion: the transition from symbolic AI to machine learning and neural networks during the 1980s and 1990s was a turning point. That coma rejuvenated the field after the setbacks of the AI winter. The backpropagation breakthrough not only resurrected interest in neural networks, but also transformed AI research into a dynamic, data-driven discipline. The advancements made during this period established the methodological underpinnings that are now central to modern AI. Through the fusion of theoretical innovation and practical application, the lessons learned in these decades have paved the way for the powerful, versatile AI systems we see today.